Hello, in this episode we'll be looking at GDB and debugging a strip binary. Here I have a simple C program which includes std.io, declares an int a equals 5, compares a to 6, and if it equals 6, it prints hello. So typically when you debug program you're building yourself, you try to build with symbols, debug symbols. For example, with GCC or Clang, you pass the G flag, then the name of the file, you can pass an output name. And here we have our output, which is you check this, layout, which is an ELF file, debug with debug info, not stripped. And if you try to run this into GDB, you can see that it's reading symbols from A out. You can typically break on main, or you can use the start instruction, which will create the breakpoint in main and then start the application and stop at the breakpoint. And it'll show you the source code, the corresponding source code. You can use N to go to the next line, and it'll still show you uh, the corresponding source. However, with the strip binary, if you remove the G flag and then strip the binary, if you try the same thing with GDB, it'll tell you no debugging symbols found. If you try to break main, it'll tell you function main not defined. Same thing with start. So how do we go debugging this binary? You can use the start I, which starts at the first instruction, and then you can go info file. This will show you the entry point for your application. We'll copy this entry point. So the entry point does not actually correspond to the main function. To break into it, we'll pass a star to dereference this address, and it assigns a breakpoint at this address, and we can continue, and it breaks at this address. You can display the next, you can see that it does not show the instructions that are running. However, you can display them with each uh, operation, next or step into operation using step display I, and you pass the program counter, which corresponds to the register, the RIP register, which is the instruction pointer on an x86-64, and it'll show you the corresponding assembly. If you pass next instruction, if you pass next, this will fail since it cannot find bounds of the current function. You can pass NI for next instruction. You can also pass SI for a step into next instruction, which is useful for call instructions, assembly call instructions. So if you pass NI, you can see that it shows you the next instruction. We also, I prefer using the Intel syntax for assembly. So you can tell GDB to prefer the Intel syntax, this assembly. Also, GDB has auto completion, flavor till. And if we go and I again, it'll show you this is, if you notice, the AT&T syntax has the instruction and then the source with the registers actually having an percent sign before them. So the XOR EBP just zeros this register. For the Intel syntax, you get the instruction like the AT&T syntax. The first operand is the destination, and the second operand is the source, unlike the AT&T instruction. And you don't have to write the percent signs. Also, it simplifies the instruction names. For example, for Intel syntax, a move instruction is just MOV. For the AT&T syntax, it depends on the actual size of the operand. So it's move Q or move L, etc. You can display the next several instructions, for example, 20 instructions, also using the program counter. So the I here is instructions, similarly to the display I. You can also have a GDB init file to just tell GDB to use these following things. By default, you can have them on a project level by having a local.gdb init file or on a system level. So this command shows us the next 20 instructions. You can see that when we pass an I, for example, it shows us this instruction, shows the arrow at this instruction. If you just press enter, it will just execute the last instruction. So if you just press enter, so it executed also next instruction, and we are now at the move RDX RSP. So we're still not in our main function. Usually there's some setup code that runs before main, and then usually you get a call to our main function, which is most likely this call. So if we go next, 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 and here we're at the call, and if we try to step into it, you can see this calls libc start main impl with the address of the main function. So in a strict binary, usually you don't get any symbols. However, GDB recognizes the address of the libc start main impl from the procedure linkage table. And we can actually use it to break right into it instead of, for example, starting and finding the entry point and going next until we find this. So if we just exit, we'll create a GDB init file. And let's tell GDB to set the disassembly flavor to Intel and to always display one instruction at the program counter. And let's start GDB again, the same binary. And we'll use the break libc start main. And it'll tell us that there's no symbol table loaded. Do you want to create the breakpoint pending on a future shared library load? We'll tell it yes. And then we'll just type R for run. And I'm not sure what happened. We run into a fatal error, internal error, JDB. So we'll try again. So break C start main. Yes. Then run. And we reach the our breakpoint here. We can use this address to access the main function. You can, as you know in C, you can have a main function with an int argc char argv, which is an array of char pointers, which represent the number of command line arguments. You can see argc here is one argument, and this is the address of the argv. If you remember from our program, we didn't have the int argc char double star argv. So what's the first argument? You can actually poke into these. Just first copy this and break here, and then we'll tell GDB to continue. And we're now at the main function. So let's query this argv. You can actually tell GDB to print the address or the value at the address. You pass this. So this will just give you an integer value, the equivalent of this. However, we actually need to uh, tell it what type it is and also dereference it. So the first argument is the address of the application that we're running. And let's check the instructions in our main function. And you can see our assembly here. It starts with our typical function prologue and ends with the typical epilogue. Which is push RBP to the stack, move the value of RSP, the stack pointer, to RBP, the base pointer. It'll sub the RSP by 10. So these are always shown in hex value. Another cool thing in GDB is that you can actually check. You have a Python interpreter basically. So for example, we don't know what 0x10 means, and you want to know what it is. So you can use Python print int, and this is base 16, so it's hexadecimal, and this equals 16. And you can see that here, for example, we move the value 5 into this address. As you know, the stack grows from in assembly or in actual machine code in an inverse manner. So we move the 5 value here into this address. So if you want to, for example, check what the value at this address is, you will actually have to reach it using the assembly, using, for example, next I, etc. And then you can read the value here. So, for example, let's do that. And I again. So we're actually here, we're moving the 5 into this address. So let's print this, for example. And this is actually an int pointer, and we dereference it. We can tell, you can use the RBP minus 0x4. And this is the value 5. And here it does a comparison to the number 6, which is equivalent in hex and decimal. And if it's not equal, it'll just uh, jump to this address here, which is here, which assigns EAX, which represents our return value, to 0, and leave the function. Otherwise, it'll just go to this instruction here. It loads this address, which is a static address in our binary, which is represented by the RIP, the instruction pointer, and a fixed address in our assembly or in our machine code. It loads it into RAX. It moves RAX into RDI, and it calls puts. So if you know, usually the first uh, argument to any function is passed into RDI, the next argument RSI, RDX, RCX, etc. So here puts only takes one argument, and this argument is in RDI, and then we call puts. So if we print the assembly here, we're actually at the compare. We didn't run into it yet. We're stopped just at this instruction. So let's, for example, change the value. This was, as we've seen, 5. Let's make it 6. Set equals 6. And then let's go to the next instruction. So this is now false. Next instruction. So we've actually entered into the condition here, and it read this address or the print itself, the address of the string itself into RAX. For example, if we wanted to check the value of RAX now, so this is a const char. You can see the value hello. And if we continue running, you can see that it printed hello. And I've shown you, for example, how here you can pass some Python code into the GDB shell. You can also pass multiple lines of Python, and this will start several. Um, you can enter several lines, print hello, for example. And to actually get the Python running, you have to pass end, and you get hello here. That's basically it for this video. Thanks for watching. I hope you enjoyed. Bye bye.